A mole is one of the most important concepts in chemistry. It is defined as the amount of a substance that contains the same number of particles as there are atoms in exactly 12.000 grams of carbon-12. These particles may be atoms, molecules, ions, or formula units, depending on the substance we are dealing with. The idea of a mole is very similar to other counting words that we use in daily life. For example, when we say a pair, we mean exactly 2 items. When we say a dozen, we mean exactly 12 items. In the same way, when chemists say 1 mole, they mean exactly 6.022 times 10 to the power 23 particles. This very large number is called the Avogadro constant, and it gives us a bridge between the very tiny world of atoms and the larger world of measurable grams and liters. Why is the mole concept so important? Atoms and molecules are extremely small, and it is impossible to count them directly. For example, even a single drop of water contains more than 100 billion molecules. Since it is not possible to count them one by one, chemists use the mole as a counting unit. By measuring the mass of a substance in grams, we can calculate how many moles it contains, and from that, how many atoms, molecules, or ions are present. The molar mass of a substance is the mass of 1 mole of that substance. It is measured in grams per mole. For an element, the molar mass is equal to its relative atomic mass in grams. For example, the relative atomic mass of carbon is about 12, so the molar mass of carbon is 12 grams per mole. For compounds, the molar mass is the sum of the atomic masses of all atoms in the formula. For example, the molar mass of water, H2O, is 18 grams per mole, because each hydrogen atom has a mass of 1 and oxygen has a mass of 16. So 2 plus 16 equals 18. The relationship between mass, moles, and molar mass is given by the formula number of moles equals given mass divided by molar mass. This formula allows us to convert between the measurable mass of a substance and the number of moles it represents. Another important formula is number of particles equals number of moles multiplied by the Avogadro constant. With this formula, we can calculate the exact number of atoms, molecules, or ions present in a given amount of substance. Let us see some examples. Example 1. Suppose we have 18 grams of water. The molar mass of water is 18 grams per mole, so the number of moles equals 18 divided by 18, which is 1 mole. This means there are 6.022 times 10 to the power 23 molecules of water in 18 grams. If we want to know the number of atoms, we multiply further. Each molecule has 2 hydrogen atoms and 1 oxygen atom, so in total, there are 2 times 6.022 times 10 to the power 23 hydrogen atoms and 1 times 6.022 times 10 to the power 23 oxygen atoms. Example 2. Suppose we have 0.25 moles of carbon dioxide. The molar mass of carbon dioxide is 44 grams per mole, so the mass of this amount will be 0.25 multiplied by 44, which is 11 grams. The number of molecules is 0.25 multiplied by 6.0. 2 times 10 to the power 23, which is 1.505 times 10 to the power 23 molecules. Example 3. Let us take sodium chloride, common table salt. The molar mass of sodium chloride is 58.44 grams per mole. So if we take exactly 58.44 grams of sodium chloride, that represents 1 mole. In this 1 mole, there are 6.022 times 10 to the power 23 formula units of sodium chloride. Each formula unit contains 1 sodium ion and 1 chloride ion, so the number of sodium ions is 6.022 times 10 to the power 23, and the number of chloride ions is also the same. There is also a special relationship for gases. At standard temperature and pressure, which means 0 degrees Celsius and 1 atmosphere pressure, 1 mole of any ideal gas occupies a volume of 22.4 liters. This means that whether we are talking about hydrogen, oxygen, nitrogen, or carbon dioxide, 1 mole of any gas at these conditions will fill exactly 22.4 liters of space. Some modern definitions use 1 bar pressure instead of 1 atmosphere, which makes the volume slightly different, about 22.7 liters per mole. This simple rule makes calculations involving gases much easier. For example, if we have 11.2 liters of oxygen gas at standard conditions, that corresponds to half a mole. The number of molecules is half of Avogadro constant, which is 3.01 times 10 to the power 23 molecules. Since each oxygen molecule has 2 atoms, the total number of oxygen atoms is double this number, that is 6.02 times 10 to the power 23 atoms. It is very important to be careful when counting particles. For covalent substances, like water or oxygen, we count molecules. For ionic compounds like sodium chloride or calcium carbonate, we count formula units and ions. For metallic elements like sodium or copper, we count atoms. The mole concept is therefore the foundation of all stoichiometry in chemistry. It connects the microscopic world, which we cannot see or measure directly, with the macroscopic world, that we can measure in the laboratory. Without the mole concept, it would be impossible to write balanced chemical equations, to calculate the quantities of reactants needed, or to predict the masses of products formed. In summary, a mole is not a mass, and it is not a size. It is simply a counting number, just like a dozen, but enormously larger. 1 mole always contains exactly 6.022 times 10 to the power 23 particles, no matter whether they are atoms, molecules, or ions. By using the mole, chemists can easily switch between grams, liters, and numbers of particles, making chemical calculations possible and accurate. This image is about the mole concept in chemistry. It shows 2 balances, each with a pile of atoms on top, representing different elements. On the left side, we see carbon atoms, each with an atomic mass of 12. On the right side, we see copper atoms, each with an atomic mass of 63.5. Both balances are showing the same number of atoms, which is 6.02 times 10 to the power 23. This number is known as Avogadro's number, and it is the number of particles present in 1 mole of any substance. Now let's understand what this means. Even though the atoms of carbon and copper are completely different in size and mass, 1 mole of each contains the exact same number of atoms. In other words, 1 mole of carbon has 6.02 times 10 to the power 23 atoms of carbon, and 1 mole of copper also has 6.02 times 10 to the power 23 atoms of copper. The number of atoms is equal, but the masses are different because copper atoms are heavier than carbon atoms. This is why the image shows that 1 mole of carbon atoms has a mass of 12 grams. 1 mole of copper atoms has a mass of 63.5 grams. The reason for this difference is that the mass of each atom is linked to its atomic mass. Carbon has an atomic mass of 12 atomic mass units, so 1 mole of carbon weighs 12 grams. Copper has an atomic mass of 63.5 atomic mass units, so 1 mole of copper weighs 63.5 grams. In other words, the mole equalizes the number of particles, not the mass. No matter which element you are looking at, 1 mole always contains 6.02 times 10 to the power 23 particles. But the actual weight of that mole depends on the type of atom or molecule. This is the beauty of the mole concept. It allows us to compare very different elements on the same scale. Using moles, we can say that 12 grams of carbon and 63.5 grams of copper contain exactly the same number of atoms, even though the atoms themselves are different in weight. So, the key message of the image is, a mole is a fixed number of particles, Avogadro's number. The mass of 1 mole is different for each element, depending on its atomic mass. Carbon, 1 mole, 12 grams, copper, 1 mole, 63.5 grams. But in both cases, the number of atoms is the same,